My daughters and I recently finished building these models of Platonic and Archimedean solids. They worked out super well and we had a lot of fun with them. But I have to admit, they didn't do one thing that I was hoping they would. They didn't give us a good intuition for why there are 5 Platonic and 13 Archimedean solids. So I came up with an alternate approach over the last couple of days and it worked out really well. So I'd like to show you. So here's what worked for me. I used this piece of notebook software called Jupyter to write some Python code to convince me why there are 5 Platonic and 13 Archimedean solids. To get started with that question, we need to know what is a Platonic solid and what's an Archimedean solid. Well, they're these 3-dimensional shapes that you can build using regular polygons as the faces. Remember, a regular polygon is just one with the same length of sides and the same angles at every corner. And you glue a bunch of these together, and hopefully you can make a 3-dimensional shape, but not always. So the difference between the Platonic solids and the Archimedean ones is for the Platonic solids, you use just one shape face. So all squares, all triangles, whatever. For the Archimedean ones, you can combine a bunch of different shapes and see if you can make something. So there's one more thing about that. To be Platonic or Archimedean, they also have to be uniform. That just means at any vertex, which is just a fancy word for a 3-dimensional corner on one of these shapes, you have to have the same set of polygons around that corner as with any other corner on the whole shape. So if you imagine yourself looking at one of the corners, like this, and then rotating the whole thing to look at a different corner, it has to look the same as the first one you started at. So now we understand what makes a 3-dimensional shape, Platonic or Archimedean. How can we figure out how many there are? Well, we need a way to label each shape to say this one's different to that one. Since we know that every vertex on one of those shapes has to be the same as any other vertex on the same shape, we can label that whole shape by just looking at what's happening at one vertex. And what I mean by what's happening is what are the polygons that surround that vertex. So again, imagine the middle of this is one of the corners of the polyhedron. We could label this as triangle, square, pentagon, right? That would be, in this labeling, that would be 3, 4, 5. Defines that whole polyhedron, if these do fit together to make one. So if you take a look at this, the Wikipedia page on Archimedean solids very helpfully lists the vertex configurations. So if you scroll through this table, you'll find some of them, by the way, have delightful names to say. I just love saying these. Rhombicosidodecahedron. That one's really fun to say. And that one's got a vertex configuration of 3, 4, 5, 4. That means if I'm looking at any vertex of the rhombicosidodecahedron, I'm going to see a 3, that's a triangle, then a square, 4, then a 5, a pentagon, and then a 4 again, another square. So let's use that Wikipedia page to build our very first piece of code. Because as we discover these solids, we're going to want to know what their names are. Let's build a mapping in Python of vertex configurations to names. I'm going to speed up the next part because it's just really me copying and pasting stuff from that Wikipedia page, and you don't want to watch that. All right, so now that we've got this mapping, let's define a little function that just tells us the name of a vertex configuration. And if we don't know its name, we're going to give it the name unknown polyhedron. Now you might notice there's one more thing that we need to do here, really. If we choose a vertex configuration like this one, this is called a cuboctahedron. Again, fun name to say. This is 3, 4, 3, 4. Triangle, square, triangle, square. But what if I asked for the name of 4, 3, 4, 3? Well, that's also a cuboctahedron. I just started at a different one of the polygons when I was naming it. I just have to rotate that vertex. Right now, if I ask for the name, it's telling me unknown polyhedron. So I need to give this function a bit more intelligence to know that I can just rotate that vertex configuration and it should still tell me the same name. Let's make that fix. So I'm going to rotate the vertex just like this. What we'll do is we'll sort all of these possible rotations and we'll choose the first one. This is called lexicographic order. Just means that the smaller numbers are at the start once I've sorted them. So let's try that again. There we are. 4, 3, 4, 3 is also a cuboctahedron. Okay, just one more thing we actually have to pay attention to here. Let's choose this one. If you look at the truncated cuboctahedron, that's got a vertex configuration of 4, 6, 8. A square, then a hexagon, then an octagon. What if I asked for 8, 6, 4? Okay, so right now that gives me unknown polyhedron, but it shouldn't. See, if I just reverse that vertex configuration, that is a truncated cuboctahedron. This is like if I'm flipping it or looking at it in a mirror, it's the same shape, right? That doesn't change, just mirroring it. So let's add some more, just a little more intelligence to know that those are the same thing. Here we go. This is how you reverse something in Python. We'll add that to the list of rotations, and again, we'll pick the first one in the sorted list. Okay, there. Truncated cuboctahedron for 8, 6, 4. Perfect. Okay, so now we've come up with this way of naming vertex configurations. We need a way of telling, is a vertex configuration possible? Does it make a Platonic or an Archimedean solid? And it's pretty tricky to come up with rules for that if you can't visualize your vertex configurations. You need to be able to draw them. But since we're working with code here, we want the code to be able to draw them for us. So a really great way of drawing stuff like this is something called turtle graphics. Maybe you've played with that before. If you never have, you absolutely should. It's a really great way to get an intuition for two-dimensional geometry. So unfortunately, this Jupyter notebook doesn't come with an easy version of turtle graphics, but it's okay. Turtle graphics is so easy, I decided to write my own here. So it's very simple to get something called a canvas in Jupyter, something you can just draw on. So let's install that. It's called IPyCanvas. So to begin with, let's have some colors because we want each face in our vertex configuration to be a different color so we can easily tell them apart. Let's just do a list of rainbow colors here. Great. So we'll need some kind of reset function. Let's start with that. That just gets our canvas ready to be drawn on. Let's give it a width of 400 pixels and a height of 400 pixels. Let's say this turtle that we're drawing with starts in the middle of the canvas, and at first its heading, the direction it's pointing in, is 0 degrees. So again, if you've never played with turtle graphics, it just lets you give very simple commands. So you could say, you could tell the turtle to move forward a particular amount, or turn left or right by a particular angle. And you can draw interesting shapes that way. So what do we need to have turtle graphics? We need a left command. Let's build that. That just subtracts an angle from our heading. And we need a right that adds an angle to our heading. So that way we can turn the turtle. Now we just need a forward command. that moves the turtle forward and draws a line as it's doing that. If you've ever done any trigonometry, you probably know how we're going to update x and y here. If you don't, just trust me on this. When you do get to trigonometry, you can think back on this and maybe it'll all make sense. Okay, so now in theory our turtle can move around the canvas and draw things. Let's teach it to draw regular polygons, like this, because these are the face shapes that we're going to use to make our polyhedra. So we're going to build up a list of the points that our turtle is going to visit. We want it to draw a certain number of sides. We'll append each point it visits to this list. I suppose we could say we'll move forward, say 50 pixels at each side. And then we have to turn to draw the next side. I'm actually going to say if we haven't drawn the last side, we're going to turn left. We have to turn left by an angle that makes it so that when we've drawn all of the sides, we've gone through a full 360 degrees. So that's actually something called the exterior angle of a polygon. So we'll make a function to give us that. Obviously, it's just going to be 360 degrees divided by the number of sides in the polygon. IPyCanvas has these nice things that will just draw a polygon on the canvas given the set of points at the corners. Let's give it a fill color, outline it in black. Okay, that should do the job. Let's try it. Okay, yeah, that seems to work. Great. Okay, so now we can draw polygons. We need to draw a vertex, which remember is just the corner of a polyhedron. It has a bunch of polygons around it. So let's define that. We'll take a list of the numbers of corners in each polygon. Let's be a bit nice here. We'll print out the name of the vertex before we draw it. Okay, so we'll reset the canvas. We'll use Python's zip function here to take a list of the faces and a list of the colors, pair them up, and then each polygon gets drawn with a different color. Okay, but we can't just draw the polygons one after another. We also have to keep track of the direction we're facing in. So we want each next polygon to be drawn glued to the previous one. So that's actually why I said we're not going to turn if we're drawing the last side of the polygon. Because we want to keep the turtle facing the way it was when it drew that side. Because now to glue the next one to it, we have to reverse our direction. That's just the same as turning by 180 degrees, right? Okay, great. Let's try that. Good. Okay, so the last thing I want to do here is I want to put a nice little dot in the middle that marks the vertex that all these faces are surrounding. Let's do that. So we'll keep track of where we started. Draw a circle in the middle. Aqua seems like a good choice. That looks great. Okay, let's test it. With say 3, 4, 3, 4, our cube octahedron. Fantastic, that looks good. Okay, so the way you should think about these when you're looking at them on the screen is this is one vertex of the cube octahedron. These are the faces that surround that vertex. And if I could just reach into the screen and pick this thing up, then I could bend the faces into three-dimensional space so that this triangle and this square touch each other. And then I'm holding one vertex, one corner of a cube octahedron. Now all I have to do is make a bunch more of these, stick them together, and I have the complete cube octahedron. Okay, so that should really help us to think about which of these configurations are possible. This one is, it's a cube octahedron, but actually most configurations that you can imagine, they're not possible. They don't make polyhedra in 3D space. So let's try to start eliminating some possibilities. Well, to start with, I think it's really easy to see that you need at least 3 faces meeting at a vertex. Otherwise, I mean, obviously you can't just have one. If you try to have two, so this is our vertex and these are our two faces, when you bend them into 3D space, they just sandwich into each other. There's nothing three-dimensional. That doesn't make sense. You've got to have a corner with at least 3 polygons on it to make something three-dimensional. Let's add a rule in our code to check for that. So we'll call it check has enough faces. Dead simple. If we have fewer than 3 faces at our vertex, then we'll reject it. Okay, so now we've got that rule in place. Let's look at a particular vertex configuration that has 3 faces around it, but this is one that's impossible. This is the first one that I found that has this particular pattern. It's 3, 5, 4. So a triangle, pentagon, square. So I was looking at this and I noticed it's impossible and there's a good rule for this. So take a minute to think about it. Look at this configuration, pause the video maybe, and see if you can come up with your own argument for why this one should be impossible. Okay, so if you managed to come up with your own reason, well done, good job. If you didn't, don't worry. I'm going to give you more opportunities to think about these later on in the video. So here's the reason I came up with. Look at the pentagon, the orange one here. We've got 2 other face shapes available to us, and we have to arrange them around the pentagon so that everything looks the same at each vertex. So if we start at the red triangle, let's say, and move counterclockwise, we're going to have a square on this face, another triangle on this face, another square on this face, but now we've got a square next to a square. This vertex doesn't make sense. It doesn't follow that same configuration that we're supposed to have at every vertex. So this shape is impossible. It can't make a uniform polyhedron in 3D space. The nice thing about this rule is it actually generalizes really easily. If we had one odd-sided polygon as one of our faces and 2 other polygons that are different to each other, I hope you can see that the exact same reasoning shows us that that's going to be impossible, right? You can't alternate around the sides of that odd-sided polygon. So what's our next rule? It is that if you have 3 faces, one of them's got an odd number of sides and the other 2 are different to each other, that's not possible. Great, so let's add that rule to our check. Let's move the check out of the vertex function now, and we'll call that check vertex, okay? And we'll call the check not odd and 2 distinct, if that makes sense. So we'll return false if we get this kind of configuration. Okay, great. We'll test it for 3, 5, 4. Perfect. All right, so the next thing I want to do is try to convince you that you actually can't have a face with 12 or more sides. Because if we can do that, then it reduces our search space, right? We don't have to look at all these polygons with more and more sides. So let's see, why is this? Let's start with some really simple examples. What's the simplest? I would say it's if you have 12, 3, 3. Right, a 12-sided polygon and then 2 triangles. Well, actually we already have a rule that covers that. 1 odd-sided and 2 other distinct face shapes. Can't happen. Let's try adding another triangle. So we've got 12, 3, 3, 3. It doesn't break any of the rules that we've got so far, and actually this is an interesting one. So by any set of rules you can come up with, this seems reasonable, and you can actually build it, but it's something called an antiprism. So if you have any polygon, any number of sides, and you surround it by triangles like this, and glue on another one of those big polygons connected to all of the triangles, you have something called an antiprism. It does exist in 3D space, you can build it, but we explicitly exclude that from Archimedean solids. Seems kind of unfair because it's followed all the rules. Why do we do it? I think ultimately it's because these are pretty uninteresting shapes. I can build one with however many sides I want on that main polygon. There's an infinite family and they're not particularly different from each other. So we just exclude them. Let's add a rule for it. No antiprisms. So we'll call this not antiprism. If we have if we have a configuration of the form n followed by 3 3s, that's not allowed. Okay, what's the next thing that we have, that we could have, that starts with a 12-sided shape? I think it's 12 and then 4 3s. So let's see what happens if we draw that. Oh, okay, so what happened? Now the fourth triangle is actually overlapping onto the 12-sided shape. So is that possible? Well, no. I have one here that I built, a physical one, and look, there's just no way to fold this into 3-dimensional space. Actually, if you have any kind of overlap here, that's called not having an angle deficit. So the ones we've looked at so far had an angle deficit. There was a gap between the faces. This one doesn't have that gap, and that makes it impossible to fold into 3D space. So that's a good rule to add. Let's go ahead and add, let's call it check has angle deficit. Okay, so how are we going to calculate that? Well, for each of these faces in our vertex configuration, we can compute the interior angle of that face. The interior angle is just going to be, if you look at this diagram, look here. So a straight line's 180 degrees. This interior angle here is just going to be 180 degrees minus the exterior angle, which we already talked about. Okay, so back to has angle deficit. We can just add together all of the interior angles on all of the faces. And if the total we get adds up to something bigger than 360 degrees, or even equal to 360 degrees, then we don't have an angle deficit and we can't fold into 3D space. Great. Okay, on to the next one. I think we've eliminated everything starting with 12 and then a triangle. Let's see, how about 12 and then a square? Well, we can't have 12, 4, 3, because we already have a rule for that. That's one odd-sided face and two distinct faces. How about 12, 4, 4? Okay, so again, this is very similar to the antiprism that we already saw. This is actually called the prism. So just like with antiprisms, we kind of think of these as a bit boring. There's a whole infinite family of them. They're not particularly different from each other. They're boring. So we'll exclude them. Okay, what else could we do starting with 12 sides? Let's try 12, 4, 4, 4. Okay, no, because no angle deficit. So let's move on to 5 as our second shape. 12, 5, 3. No. One odd-sided, two other distinct. 12, 5, 4, same thing. 12, 5, 5 has no angle deficit. 12, 6, 3. One odd-sided, two other distinct. 12, 6, 4, no angle deficit. So I believe we are done. And so we've shown that if we start with a 12-sided polygon, we cannot build a uniform polyhedron. Good. Okay, so now that we have a search space let's start searching it. So we want a number of faces around each vertex. Each face has somewhere between 3, a triangle, and less than 12 sides, okay? Oh, one more thing. How many faces can we have around a vertex? Well, by our angle deficit rule, we want to look for what's our smallest possible angle deficit, and then put a bunch of that polygon together and see what's the smallest number, what's the biggest number, sorry, of faces we could have. So a triangle has the smallest interior angle, yeah? So let's see, what happens if we put together 5 triangles? Okay, 5 triangles is going to give us total interior angles of 300, deficit of 60 degrees. Okay, that might be possible. What happens if we put together 6 triangles? Okay, so then our interior angle total is 360, which is not possible. Good. So that's an upper bound on the number of faces that can be around any vertex. It's 5. Okay. So now let's build up this space of, we'll call them candidates that we're searching through. Number of faces can be anything from 3 up to, but not including 6. And to get these candidates, we're going to use what's called a product of the list of faces. Okay, 3 up to 11. Good, and we want n faces, that's this repeat. We want the product, good. That's going to give us a list of all the possible candidates that we could get. Let's just see how many there are. Okay, 66,339, that's a lot. But it's finite, right? And for a mathematician, that's a really good thing. Now let's try adding in our vertex check with our current set of rules, seeing what that gives us. Copy paste. Okay, how many does that get us? Oh wow, far fewer, 178. We're making great progress. Okay, I think before checking the vertex configuration, we should make sure it's properly rotated, right? Because some of our rules probably depend on that. Here we go. Okay, so now we're down to just 39. Remember, our target is 18. 5 Platonic and 13 Archimedean. So we're actually getting pretty close. Let's have a look at some of these 39 candidates. There's few enough now that we can actually investigate each one of them. Okay, so here we go, a bunch of recognizable names and a bunch that are unknown. Let's start with this one, 3344. Let's draw it. Okay, so now let's think about this. This didn't have a name, so there's a reason why it's impossible. Pause the video and see if you can come up with something. Okay, so here's what I came up with. If you consider these 2 triangles, the red and orange, so you've got the red triangle and then the orange triangle, if you go counterclockwise. Okay, but now let's switch to a different vertex. Let's take this one at the bottom right of the red triangle. That's supposed to look the same vertex configuration. So that red triangle on this vertex can be either the first or second triangle in that same configuration. But that means there has to be another triangle glued to this red one on one side or the other. Okay, but now switch your attention back to whichever vertex out of those 2 has 3 triangles now in common. That's a bad sign. We now have a configuration that's got 3 triangles on one vertex, right, which is not the configuration that we were looking at. So this is impossible. Great, let's go add a rule for that. So I think we're really saying that 3, 3, and 2 other numbers is not possible as a vertex configuration. We'll call that check not 3, 3, and m. Okay, great. We can add that to our overall check. Good. Let's go back down now to where we were doing the counting. Aha, now we're down to just 28. So only 10 of these are not possible. Good. What should we look at next? Here's the next one that's an unknown. It's 3, 4, 3, 5. A triangle, square, triangle, pentagon. Okay, so why should this not be possible? Again, pause the video, have a think for yourself, see if you can come up with a reason. Okay, so here's the reason I came up with. If you look at this green pentagon, you have a yellow triangle glued to it. You can see from this vertex configuration, there's no more polygons joined to this vertex. So this red triangle has to be joined up, glued to that pentagon. So that means actually every side of that pentagon is going to have a triangle attached to it. Okay, but now look at this vertex. It's supposed to be the same as any other vertex. It's already next to two triangles and a pentagon. It also has to be next to a square. So there's a square here. But now that vertex is next to two squares. That's not possible. That's not what this configuration says. I think the same logic here can apply to 3n, 3m for any n and m that aren't 3's. Same logic. Okay, so let's add a check for that. We'll call it check not 3n, 3m. Okay, add to our overall check. All right, let's go back and update the counts. 19, so close. There's only one of these vertex configurations that must still be impossible. 3, 4, 4, 5, a triangle, square, square, pentagon. The last remaining one that's impossible. We have to figure out why. It's kind of annoying actually that there's just one by itself that we're going to have to come up with a special rule for. But let's see what we can do. Okay, so we've got triangle, square, square, pentagon. So let's shift our attention to, say, this vertex. That's supposed to look the same as the blue vertex that we're looking at. So there has to be a square here, say, and a pentagon, say, here. Okay, but then that means we've got two pentagons right next to each other. That's wrong. That doesn't work for this configuration. I think that's enough to explain why this configuration doesn't work. Let's go back up to our checks and we'll add a check just for this one configuration. We'll filter that out, add it to our overall check, and let's go back to where we were doing the counting. Boom. Okay, 18. Perfect, and we're done. Okay, so there's some follow-ups to this that I'm kind of fascinated by. Maybe if you have ideas, you can put them in the comments. Mostly I'm interested in, could we have done this with fewer rules? Honestly, I'm quite pleased with how few we have, and I think they're fairly intuitive. So we eliminated configurations that don't have enough faces, ones that don't have an angle deficit, prisms and anti-prisms, the one odd and two other distinct. That was quite nice and tidy. And then just these three other arguments. It'd be nice if we could combine some of these, wouldn't it? And I think this one is the most frustrating. That just has a single configuration by itself. Maybe if you think about it and play with this, you can think of a way to fold some of these into each other. So I've actually saved this notebook to a Google Colab. It's the exact same kind of notebook, and it's linked to in the description. So play with it. I'd encourage you to do that. You'll build up an intuition for these shapes, and maybe you'll come up with better rules than the ones I found. And if you do, post in the comments and let me know. All right, that's it. Thank you for watching.